This information is brought to you by Charles Sturt University.
With yesterday in terms of the probability was looking at the probably for different hands in poker. And essentially what that boils down to being is we've got a bunch of options that we've considered for the different hands and looked at the probability of each of them. So it really is what's called a probability distribution. So I want to talk more about those and some of the useful things you can do with them. So basically, if you have a bunch of outcomes which are all mutually exclusive, like the poker hands were supposed to be, then we know the total probability is 1 and we sort of itemise all of them. So just as a simple example, much easier than the poker one, so in a game show you get to pick different suitcases, so this is all deal, no deal, or based on at least. So 26 cases, I'll make it simpler. They have different colours to them, so the green suitcases, if you've ever watched the program, are the ones that have lots of money in them. Red in between, the blues are the ones you don't really want to win. So that's the description of it. So you can have some of each. So you have to pick a suitcase at random. You've got no idea which one you're picking until you open it up later on. What's the probability distribution? Just the colour alone for the moment. Let's not worry about the money. So you just write down the various options, so blue, red, green. Now look at the probability of each of them. So what's the probability for blue?
1/2.
So I'll just... So there are 13 choices out of the 26, or 1/2 I should say, for blue. Red is
9 out of 26.
9 out of 26, and green is 4 out of 26, which you can simplify down if you want to. So that's just an example of a probability distribution. Now, that's one idea. You could also get the probability distribution for the actual numerical values. So you get the value. Does everyone remember the game Deal or No Deal? So you have to pick lots of suitcases and you have to... So you might at one point in time going, well, there's 26 cases out there, 25, apart from the one you've got in your hand. What's the expected value I get? What's the average value of all suitcases? And at any point in time when you start losing suitcases, what's the expected value? And so when someone makes an offer in the game, should you accept their offer or should you keep playing? That's always the mechanic of the game. And knowing what the average value expect, or the expected value to get, is important. And so having the probability distribution of the numerical values and being able to do things like working at the expected values would be an important way of playing that game.
Should this squeeze?
Well, in theory it would. In practice, because they want you to keep on playing, they always offer you a lot less money than you would get. So if you go in with a big team of people into a game like Deal or No Deal, or lots of you play it over and over again, your best way of winning the most money is to never take a deal in that game. That doesn't work for individuals because you might end up with the 50 cents that way, or whatever it might be. But if you go as a team, lots of you going in as a team to make more money that way. Just how they play, just how they set the game up. Because in the interest of TV, they don't want to make a deal at the very first round. It doesn't make very interesting TV. So, but yeah, so you can do lots of probability distribution. So colour's just the simple one, make it easier, but you can do it for the numbers too. So in order to represent a probability distribution, we need to have something like a table, like that. And so pretty much, we'll mostly consider numbers rather than categories like here. But essentially what we need to do is for each category or each number we want to consider, we have a probability next to it. So we're going to consider discrete variables in this case, because we're doing a subject called discrete mathematics. You can do similar things for continuous ones, but we won't go into that. It's a little different, so it's just easy to say we won't do it today, or ever, in this subject. So we sometimes you want to consider lots of different numbers. So instead of writing a whole table out, it's sometimes useful to have formulas for it as well. So instead of having it'll have a formula to write down what the probabilities might be. And I'll look at two special cases of that a bit later. So that's what we've got to go. So that's probability distribution. I mean, as I said, from the deal or no deal situation, you might want to work at like, well, what's the expected value? What's the average value you expect to get from it? And the other thing is important to know is, well, you don't always get the average you get. Someone's a bit below, someone's a bit above. How variable is it? How likely is the nut value to be quite fixed, or is it really spread out? Those are the sort of questions you might want to have. So being able to look at those sort of ideas is important. Where would you ever consider probability distributions in what you're looking at? So I've got two here, so that's the first example. I'll just spin out. Suppose you know that you've got you actually can work out probability distribution for the different sizes of files you might get coming up, people trying to upload to a system, like the e-system that we've got here at CCU, for example. And then you have a probability distribution for the times of days people try to upload the files.
11:59.
I suspect there's sometimes more common than others, that's right. And so you can work out from that what the peak times are. So what time would have the highest load to the system, etc. And is the load, at those peak times, the load sufficiently high that you need to perhaps do a second server or release more resources for it? That's sort of the modelling you might want to consider. And it's random. You don't exactly know when people are going to do it, but you can look at historical values to get the overall pattern, to get the sort of ideas. Another one is you're designing a game, which could be a board game like Monopoly, or it could be a computer game, and you're trying to make the game not the same every single time. And sometimes you can do that by just relying on people being different, but other times you might put a random element in the game. So Monopoly has the dice, for example. And you want to design the game, and so having a probability distribution helps you work out what's going to happen. So in the game of Monopoly, knowing as you're going around each turn, as you go around the board in Monopoly, what the expected cash flow is each turn. So should your expected cash flow should be positive or negative in Monopoly each turn? Well, if it was positive, it means there's more money coming into the system every turn, and people just get more and more money each time, which means the game goes on for a long time. If you start having negative cash flow, then people's money starts evaporating and someone's going to go bankrupt after some point in time. So if you want to make sure the game doesn't last forever, which is important, I think, for Monopoly, who likes to play for a game for Monopoly all day long, it's
only one day.
then it's important to have negative cash flow, but not too negative because someone will go bankrupt almost straight away. And so having some idea of roughly how the mechanics are going to go is important for designing the game. Now, it doesn't stop you having to actually have to play it, or modelling it by a computer and model it how it's going to go. But it gives you at least a rough idea to begin. So having some idea of probability distributions is important for lots of sort of ideas. So that's my little cell. So let's have some little language for it. This is some stats terms. So we want to consider probability distributions for numbers primarily. So when I consider these sort of things, they're called random variables. And so a random variable is a number, so hence the name variable, that is a result from some random event. So I've got two on the board. So in deal and no deal, you pick a case that has a number, so how much money you're going to get if you end up opening that case. That's the variable, and it depends upon a random event, namely you just picking something random. Or it could be you're tossing your coin 10 times. How many heads do you get? So the number of heads is a number based on a random event, hence a random variable. And so in order to describe it, if we know what the probability distribution is, which is a fancy way of saying, if you know what the probabilities for each different number we want to get, we understand it completely, we can do lots of things with it. Sometimes these random variables have nice special patterns. So for number 2 there, that's called a binomial distribution, and it has quite not well-known formulas that Excel would have built into them, and I'm sure lots of other software programs as well for that matter. So it's quite well known, and therefore you can work them out quite quickly using formulas that a computer might know. We'll do that one later. So just the notation that I'll try to use is I try to write down capital X for the random variable. And so because the variable can be lots of different things, and it depends upon what random event it is, I write capital X to represent all possible values it can take. That's the general case. And then because I need to plug in formulas and things like that, I need a placeholder for the actual value. And so I write down little x for the placeholder for actual numbers. So that would only ever be a precise value. And so I write down this thing, P capital X equals little x. That's the probability our random variable is equal to something or other. Normally, the little x is going to be something like 3 or 2. It's going to be an actual number whenever we're going to use it. And it's just that's the number we're going to plug into the formulas, essentially, when we get to them a little bit later on. So that's just what's the probability our random variable is equal to something. And just so capital X is the random variable. The little x is just some number we're going to sub in later on. Just useful for formulas. Now, I'll try to be quite precise in my lectures notes here. If you ever have to write this stuff out, I'm not pedantic about how you write it out. So I'll be try to be precise, but you may not be. It's okay. So let's work out a probability distribution for a particular random variable. So this is one of these special cases. This is a binomial distribution, but let's just work it out directly, not knowing that it has some special case to that. So you toss a coin 3 times. Let's assume it's a fair coin. So you've got an even chance of being heads or tails. That seems reasonable. And you've got to work out what's the let capital X be the number of heads. So it depends what coins cost, what you're going to get. So let's work at the probability of getting no heads, 1, 2, and 3 heads, etc. Let's work on what's the probability of getting no heads?
Half to the power of 3, wouldn't it be?
Yep. So it's
1/8.
they're 3 coins independent of each other. So we looked at independence yesterday. So it's a half the first head, half the second, half the third, and we just do a product of all 3 of them because they're independent. So it's not. So 1/8. What about 3 heads?
That's still an 8.
It's the same idea. So it's still going to be a half to the power of cube. And the reason is for no heads we're doing a tail each time, for the heads we're doing a head each time. So they sort of match up. What about for the middle 2 cases? So let's do 1 head.
Going to be like 1/2, so that's the probability of getting the 1 head, and then plus 1/2 to the power of 2 for the 2 tails.
So you might think a half for the 1 head times by a half squared for the 2 tails.
No, I said plus.
Oh, you want to have both at the same time? So it has to be multiplication.
Yeah.
That's not quite right though.
Yeah. Because that's just 1/2 cubed again.
So the reason why that's not, but you go, well, it's close because that's assuming that the first coin is the head and the other next 2 are tails. But it could be the head could be in the middle, or it could be the last one. So there's 2 other possibilities. So there's 3 possible locations we could have for where the head might be. So you can multiply that by the 3 possible places where you put the head. And so you get 3/8. Another way of thinking about it is I've got 3 different coins. I would like to choose one of them to be the head. That's the number of ways of picking the heads. Once I've made that choice, then I've got half, a 1 and a half chance of picking the head for that head position, and then 1 on 2 squared for the 2 tails. For the 2 coins, 2 heads, I've got 3. I like to choose 2 of them to be heads, so 3 choose 2. And again, similar things before. I got a half a chance of picking the heads for the 2 head position, and got a half for picking the tail. We do it completely differently. So the other way of doing it, just picking this one on the bottom here, I've got 3 choose 2 ways of getting the 2 heads. The total number of options, there's 8 different ways we can do it. Where do I get the 8 from? So 2 to the power of 3. They're all the same. So the easiest way of doing this, I reckon, is to use those combinations in the end of the day. So combinations are your friend, though we were reluctant yesterday to use them. Even this is a small case. And this is, I mean, you don't have to use it at all, but I think it still is a helpful way of trying to represent things down. Combinations are useful things. You can do cheats, of course, as well. So the 1/8 on the either side are quite easy. So therefore, the probability in the middle is going to be 6/8 for the middle 2, and it seems like they're going to be symmetric. So just split it up in half. Should be 3/8 in each. That's the cheats way of doing it. Well, not actually trying to formalize it at all, but just using the symmetry of the whole picture. So that's a probability distribution. And the best way, as I said, really is to go there's 8 possible choices all up. That's 2 to the power of 3, and it's either 3 choose 0, 3 choose 1, 3 choose 2, or 3 choose 3 are the 3 different choices. So just like we looked at counting stuff last week, just counting the number of different options. And each of them is a combination. So we might want to do things like to this side. So we want, and what we'll do in a second. So let's do some a few more, just so we've got some things to play around with. So we've got rolling 2 dice. We'll let Y be the sum of the 2 dice. So what's the possible sums you can get?
2 through 12.
Yep. What's the probability that we'll get for each of these situations? What are the easy cases to do?
Well, there's 1 in 12 of getting 2, and there's 1 in 12 of getting 12.
Not quite right.
1 in 36.
1 in 36. So
Sorry.
there are, if you do, so there's 2 dice, so it's 6 for the first one, 6 for the second. So there's 6 times 6, or 36 different ways of getting the 2 dice rolling. Only one of those methods gives you 12, which is 2 6s, and only one of those gives you a double 1, and hence 2. How many ways are there of getting a 3? So at 36 is all we've got all up.
2 and 1.
So it can be 2 and a 1 or a 1 and a 2.
So that's 2.
That's going to be 2 out of 36. What about getting a 4?
3 and 1 and 2 and 2.
So 1 and a 3, 3 and a 1 the other way around, or 2 2s.
So 1 9.
So 3 out of 36. I mean, I'll put them all over 36 to make it easier for them, but some of them do
So if
simplify.
you've got 2 and 2 and then 2 and 2, vice versa.
No, if it's 2 and a 2, you can't swap them around. That's exactly the same thing again. So 1 and 3 and 1 are different. They look different. What about 5?
No. 2 and 3, 4 and 1.
Oh, wait, no, and vice versa.
And vice versa. So there's 4 of them. You can see a pattern here, I hope. They're just going up.
Yeah, they're all over 36.
They're all over 36, yes. You can see the numbers are going up. 1, 2, 3, 4, 5. Up to 7 you get 6 on 36. So it's just a continuing pattern, it's just more and more. What happens when you get to 8?
Would it be 7 or 36?
It's gonna be 5.
Okay, it starts going down again.
I'm misled.
Yes. So the pattern breaks down at that point in time. So when you get to 8, there starts being less options around, and the reason is because for 7 you can have 1 and 6, for example. When it comes to 8, you can't have 1 and 7 because you can't roll a 7 on one dice. That's why the options start decreasing again. And if you go down, it's all symmetric. So they start heading down on the way. So what's the most common number? 7. So if you played Settlers of Catan, which I've mentioned a while back, you get the robber if you get a 7, but they have dots for each, so on the board, and they have the numbers 2 up to 12, except for 7, and they have a number of dots on them.
I get 11.
So a 6 would have 5 dots on it, because it corresponds to probably a 5 out of 36. And a 2 would have 1 dot on it, and that's just to show the relative frequency of them all. And it really it's just a more visual format of this sort of table. Essentially, is what that game does. Who's played it? Know what I'm talking about? Sorry. Half a class. That's not too bad. I mean, they do it. So and it really matches up to this exactly. So if you never played the game, it is a good game. But up to you if you want to play it or not. But don't play it in tutorials, I guess is the request.
Pull it out. Not in class, oh no.
Balls.
So this one's picking balls out of a hat. So you've got 3 red, 5 white balls. I want to pick 3 balls at random. X is the number of red balls. Let's calculate various probabilities. I think I'm going to write it differently actually. Just thinking about it, I think I need a bit more room, so I'm going to do it differently. So, for number of red balls, here we can have 1, 0, 1, 2, or 3. So that's the number of ways we can get a number of red balls we can have. So we're picking 3 balls from a hat, from a bag, I should say. So how many red balls can we get? All 0 up to 3. So to give you various names for these things, the possible values you can get for a random variable is called a sample space. So the sample space here is 0 to 3. The sample space for 2 dice was from 2 to 12. That's called a sample space. And we use that similar word, we've used it before, but that's essentially the universal set of all these options you might want to consider. So we're going to probabilities. So what's the probability of getting no reds, essentially? So the way probabilities is the number of ways of counting that possible arrangement divided by the total number of things we might want to consider. So a good thing to first consider is what's going to be on the bottom, what's going to be the denominator of all these different probabilities. And that would be the number of ways of picking 3 balls from the bag, essentially. So how many balls were in the bag?
8.
8. So I want to pick 3 of them. Is it a combination or a permutation?
Combination, isn't it?
Yeah, so
Pick it.
because we can't tell the balls apart when you pull them out, and it's just a bunch of balls really, we don't really care the order. So, and the reason is because we're just counting number of red balls, we don't care when they are, what the order they come out is, we just care if we got the balls or not. So it's just no order is required, so it's just a combination. So all of them would be 8 over 8 choose 3. Number of ways they're picking the 3 balls. So how can we get none of them to be red?
We got a 5 in 8 chance of getting.
So we've got to pick the red balls. So from our three red balls, how many of them do we want to be red? None. So we've got to choose none of them to be red. From the 5 white balls, we want to pick 3 of them. Permutation or combination?
Combination again.
Combination, because again we don't care in order. So I'm going to choose 3 from the 5. So 3 whites from the 5 whites to make up the numbers. Do we add them or multiply those two things?
We multiply them together.
So plus would be if you want to do one or the other, but no, we want them both at the same time. So because it's an AND. I'll do this in Excel in a second to get the numerical values. So it'd be 3 choose 0 times 5 choose 3 over 8 choose 3 would be that probability. What would the next one be?
3 choose 1 times 5 choose 2.
Over 8 choose 3, yep. How do you guys write the rest of them down? You've got your own piece of paper. So you write down what the bet pattern is.
No motivation whatsoever. Absolutely no motivation whatsoever.
Well, you have to do it later on for other assessment tasks. So. So let's just do the Excel to how it works. Work it out for us. So we had we want to pick from our 3 red balls, isn't it? That we've got none of them times by we want to pick from the 5. We'll pick the rest of them to be white. The probability that divided by 8 choose 3 even. So if you do the numbers, I reckon the first probability is about 18% thereabouts. And that's what the others should be. So just going down. So the number of ways of getting 3 red balls would be 3 choose 3, so pick all 3 red balls, and from the 5 white one choose none of them, so 5 choose 0. And if you do that, probably there's only one way of that happening, and divide that by the 8 choose 3 to get the probability. So if I add up those 4 numbers, what do you think we're going to get?
Probably 1.
If it's not 1, what does that mean?
Wrong.
You made a mistake, that's right. So because there should be only 4 options we'd ever consider, essentially. So let's just, what were the other ones we had? We had the heads situation, so if I want to show you. So the probabilities we had here, just these are right down, an 8. So that's what we had for the head situation, there's 2 different probability tails. So what can you do with them? So you go, well, I want to try to understand these sort of probability distributions. I want to do a few things with them. And so one way is to try to get a picture of it. So let's just do the heads example. Let's just get a picture. It's a very simple picture for it. So it's just the probability on the vertical axis and the different numerical values on the x-axis, essentially. You can often make them into spikes, but it's easier to just go to plot in Excel quickly. So it's called a spike graph, and it just gives you an overall picture. So that's the head situation. I don't want that at all. Let's do the same thing for the ball example. So they both have values 0 up to 3. So the sample space of both of these are the same, which is why I want to consider them. But so I want to say if the probabilities match up or not. And you can see them numerically, but if you do a picture, often you can see visually quite clearly. So do the pictures look the same?
Hell no.
No. So the answer is no. How are they different? I guess is the more interesting sort of question. What sort of ways can you compare these distributions?
Well,
Now, I've given you nothing at all of how to compare them, so it's just have a
if you've got a
guess.
50-50 chance with the coin, it's going to be symmetrical.
Okay.
Whereas the balls, you got 3 and 5, so it's not an even chance of picking one. So it's
So a
in
good
favour of the white balls.
Yeah. So a good observation is to notice that the heads example is symmetric. That's certainly a key observation. Where the red balls is not symmetric. And as you correctly say, there's a bias to less red balls and hence more white ones. So there's a lack of symmetry there. So symmetry is a good thing to notice in pictures. So having some sense of the shape of it, or the symmetry of it in particular, is a useful thing. Other things that are useful to look at is looking at the average value. What do you reckon the average value for the heads might be? The number of heads you might get on average. Just as a guess.
It's probably 2.
Right bang in the middle, 1.5.
Probably.
It is 1.5, definitely. Now, so on average, average values don't have to be integers; they can be fractions. What's the average value for the number of red balls? You have to really guess here. It's hard to work. Knowing the exact answer is hard. It's going to be. You can see less red balls is more likely. So it's going to be less than 1.5. So maybe 1-ish, perhaps. Interesting to look at exactly. So pictures are useful, but they show that we want to compare distributions, have a sense for them. So the sort of themes I want to consider, and you can have others, is looking at the shape, and so symmetry is the key aspect I want to consider there, which we can see in those pictures. Look at what the centre is, and the centre, you can think of the centre in different ways. The simplest way of centre is just to look at the average value. You can look at the centre in terms of pictures just for looking at the mode. What does mode mean again? You've seen it at school, which is what I'm asking. You might have seen it at school.
The middle, isn't it?
Most likely.
It's most likely. So what's the most likely value for the red ball case? What's the most likely value? Number of red balls. Yeah. 1. So it's just the probability, the highest probability, or the highest point in the graph. So there it is there. What's the mode for the heads example?
One and 2.
So either Excel would say there isn't one because there's a tie, or we would say that equally 1 and 2 heads would be equally the mode. So you can. So that's a simple way of measuring centre just from looking at the picture. But often we want to go more usefully is to look at the average value. And we also want to look at how spread out these values are. Which of those two graphs is more spread out? It's a hard question.
Vertically or horizontally?
So what I mean by more spread out, so the values are 0, 1, 2, 3. They're the 4 different values. And so things like the range is the same. Both got a range of 3. But how consistent? So more spread out means that there's much more variability in the possible numbers you can get. If all the numbers were, if you did the whole thing over and over again and you always got 1, that would be not very variable. Where if you got all numbers possible and equally, then that's the most variable you can sort of get. So which of these is the most variable?
All's 1.
Well, my guess is the heads is probably most variable because the reds value is much more likely to be 1, so it's much more strongly likely to be just one single value. It's not spread out so much. Let's do some calculations. I'm not sure we'll get through all of them today. To see actually to check it out properly. I've got to try to do the calculations, yeah. But so we'll probably do them next week to actually verify what really is the case or not. So they're just looking at something visually. Let's get some formulas behind it all. So basically, we want to get a sense of shape for it all. There's lots of different ways of describing it, but I think a good one useful way to talk about shape is to talk about the symmetry, which is what Jacob mentioned straight away. And so the words that I like to use is symmetric. So symmetric means it has mirror symmetry. So because I can make a mirror image of it and it'll look the same. That's what symmetry means. So the dice example and the heads example are both symmetric distributions. The other talk you want to talk about is being not symmetric, and there's sort of two classic ways you get things that are not symmetric, and that's called left and right skewed. And so they're just mirror images of each other. So just pointing at the picture, if you have how they define intuitively is you tend to have a peak, and if it's not symmetric, you tend to have something in balance. So you have one tail longer than the other. So here you've got, if I just sort of think of it stylistically, you've got a peak here, so those three numbers, and it sort of tails off on this sort of side. So therefore this number sort of has a bit of a tail to it. The direction of that tail is the direction of the skew. So that would be skewed to bigger numbers, or if I'm looking at it from my screen, looking it to the right. So it's called right skewed. There are numerical ways of calculating skewness. So there's just a formula for it as well, which I won't mention. You can look it up on Google quite easily if you're curious for it. But I think it's just good to get an intuitive understanding of it. It's just really the idea of looking at how peaked something is. So with the right skew, so the classic example is you've got a peak and then a really long tail. It's a really strong right skew distribution. And left skew will look the other way around. So if you looked at marks for this let's look at this subject. So marks for, I don't know, ITC 161, subject that some of you guys have done. Would the distribution of the marks be symmetric, right skewed or left skewed? I guess. We all just guessing.
I'd say left.
Slightly left skewed.
So in university, marks tend to be left skewed. That's the more common example. The reason for that being is that most people do not just university, everyone has busy lives. And so for various reasons, which may not be academic whatsoever, people have to drop out at various points in time. And so the long tail there are people that other things have got in their way, and therefore they may not have made the exam or things have got too hard. Most people do okay, that's the big bulk at the top, but there's some people who haven't got through for various reasons. Often nothing to do with academic reasons. I mean, you might break a leg or something like that really interrupt your study. Lots of different reasons. So that's
I
common.
imagine that really confused them very much. Chucking in a cast and not class anyway.
Oh, you can break it. I mean, you can break it out really badly if you wish. I hope you don't. But, so yeah,
If we test that theory in this lesson, I volunteer my leg.
So that gymnast.
Oh yeah, did you see the Rio Olympic gymnast who really messed up their leg?
yes, that'd be.
I watched a remix of that last night. It's pretty good.
I would not like to that person. Other words you might want to talk about shape is the number of peaks it has. And as I said, the peak is just a mode, effectively.
Might be like.
So if something has no peaks at all, if every single thing has exactly the same height, it's called a uniform distribution. Uniform. So if you had the deal or no deal, if you looked at the different, money values you'd get from deal or no deal, they were all equally likely. So they would have a uniform distribution, for example. If you've got one distinct peak, it's called unimodal. So it means one mode, one peak. If you had two different peaks, it'd be bimodal. And after that, you'd stop really counting and just call it multimodal. Lots of different peaks. So simple distributions like the two we've looked at, for a number of red balls, number of heads, are both unimodal, so one clear peak in them. And so they're different ways to try to describe the shape of it, just try to understand the distribution. And so if you've got one peak, everything seems to collect around that. If you start getting more than one peak, you start getting two different sorts of behaviours cropping up. Things can go in two different directions. They're harder to look at. So some subjects, like Maths 105, the distribution of the marks Maths 105 would be more bimodal, and depending upon what level of maths you've come in before. Okay, Maths 105, some of you guys done.
You got that big bunch of people who do really bad and a big bunch of people who do really good, and just kind of stumps in the middle.
That's approximately what it is. I use slightly different words to you, perhaps, but that's the intention. Yes. And it really does depend how much maths you've done before. So if you did extension 2 maths at school, then you ought to be doing.
And what are you doing here? You
Should be doing
theoretical
100.
physics.
MTH 100.
MTH 100 is much, much easier.
It's like year 10 level maths, yeah.
So maths is useful for all people, but at different levels, and so you've got to get the right level. So there's different distributions. There's different shapes. So let's just finish on looking at the centre. So as I said, you can just look at the peak as a rough guide. So the mode is a rough guide for the centre. But one more useful is working at the what's called the expected value. Most of the time we would call it a mean or an average. So they're the more common words we'd use, as you've seen for already. And it's looking at the average value. There's a form on the slide there. Let's ignore it for the moment. How did you work at average when you did it at school?
You add them all up and then you
Divide by how many you got.
Okay, so that's pretty much the idea. So you want to add up all the values you have, divide by how many there are. It's the same concept here. So if you go back to the heads example,
get them all off you.
so if you basically toss 3 coins over and over again, after a while you'd get the number, 0, 1, 2, 3. You basically get those in lots of different counts. On average, 1/8 of those times you get a 0, 3/8 you get a 1, 3/8 you get a 2, 1/8 you get a 3. If you got a bunch of values, if you did it like 100 times, for example, and added up all those values, just add a normal up like you normally do, and then divide by how many you've got, so divide by 100, that would be the estimate of the average. Right, that's exactly how you think about average. You could do the same thing here. If you do that, then approximately what you'd get is 1/8 of the time you get a 0, right? So 1/8 of all the numbers you'd ever get would be about a 0. And then 3/8 of them would be a 1, and 3/8 would be a 2, and 1/8 would be a 3. So therefore, if you add up all those numbers, then 1 multiple of that would be 0, 3 times would be 1, and then you have to divide by the grand total of 8. So another way of adding all up and dividing by the total, equivalent way would be to multiply each number by its corresponding probability. It actually boils down to the same sort of formula. So to work out an average really is about, as this formula suggests, getting each value, so getting each value x, multiplying by the corresponding probability, and then summing them all up. So this sigma sign here means
The sum of.
sum of. That's just a way of summing all over all the different x values, x times by its probability. So what I mean by that is, each case, each number, 0 up to 3, get numbers, multiply them by the probability and add them all up. And then you get the average. And in this case, because of symmetry, because it's exactly symmetric, I reckon it's bang in the middle there, 1.5, without really doing any calculations at all. But let's get Excel to do these two cases for us. So what we're going to do here is we're going to do the number times by the probability. So get each of those, and then we're going to add them up. I looked at it.
Someone's doing.
Oh, okay. Well, that's the reason, because it's not the heads and tails example. That's probably the reason why. So let's just do this one. So it's number of heads times by the probability. So basically that's doing all the different products. So this one here is 2 times by 3/8. That's 3 times 1/8. And then adding them up. And you get, like I thought, 1.5. There you go. So that's the average value for the heads example. So on average, you would expect 1.5 heads when tossing a coin 3 times. Hopefully that makes sense. If you did pulling the red balls from the hat, so on average, we'd expect 1.125 red balls from the 3 we pick out of the hat. And you go, well, there was 8 balls all up, only 3 of them were red, so not less than half. So we expect a less, what we expect on average less than that. That's how you work at expected value. So you get the number, multiplied by the probability for every single situation, add up all those things, gives you the average value. And it corresponds to the concept of average you done at school, which is adding all the numbers divided by the total. What the idea of probability is, it already has divided by the total already, effectively how it works. So it's already got the dividing by the total built into the formula, effectively. So the last thing let's talk about is you can talk about spread, and I think I want to do probably justice how I mentioned next lecture. But the idea of spread is a way of looking at how spread out or not spread out a distribution is, and we can do it for those 2 examples. But in order to actually explain it better, I won't do it in 3 minutes, so I'll do it next lecture. So those things are important to understand, and it's a good idea to give a sense for it all. So today we've been looking at probability distributions, so ways of trying to think about all possible values that you might take, and give a sense of trying to calculate them and also do things with them. So looking at the shape and centre in particular, and we'll look at spread. And then we'll look at some special cases as well, lecture as well, that might crop up in things you might want to consider.